So in this tutorial, we will introduce quality diversity algorithms that are a new family of evolutionary algorithms. So we'll be three instructors in this tutorial: Antoine Cully from the Imperial College in London, Jean-Baptiste Mouret from INRIA in Nancy, and myself, Stéphane Doncieux from Sorbonne University in Paris. So I will start with an introduction to the topic. Then Antoine will present you the main principles of QD algorithms with some examples of applications. And Jean-Baptiste will present how to scale those algorithms and most recent approaches for that, with an overview of some existing implementations. So let's start with the basics. Actually, quality diversity algorithms are quite different from usual evolutionary methods. And to better understand that, we need to come back to the metaphor that is used to see how evolution works, at least in evolutionary computation. So this metaphor has been very fruitful and has helped to propose many useful algorithms and to understand how they work. This metaphor is the fitness landscape metaphor. So in this view, the genotype is, the population is moving in a genotype space, looking for peaks of fitness. And it shows then the evolutionary process as an optimization search that tries to climb up the peaks of fitness to look for the optimal value at the top of it. So although it's very useful and it has really driven the field since its beginning, it may not be the only view of what evolution could provide. If we look at evolution in nature and all the animals and plants that have been created over the years, of the millions or billions of years, we can see a large diversity of those animals. And if we look at them from a particular ecological niche, we can clearly analyze their modification as an optimization of their capabilities. But if we look at the higher level of the whole planet, for instance, we can see many different creatures that do not compete with themselves. For instance, a shark and a bee are not really in competition. They are just completely different and they occupy different ecological niche. So this diversity is a very important feature of evolution, of natural evolution, that is not captured by current evolutionary methods. So this is one of the ideas of quality diversity, to capture this. So it forces to go from this view of evolution as an optimization method, in which we are looking for the optimal way of solving a particular problem, with as outcome a single value, towards a different view in which we are looking for a large set of points of interest. So I will define what of interest is, but let's first analyze why we may be interested in generating a set of solutions instead of an optimal value. The first motivation that was actually at the core of quality diversity algorithms is to have a better idea of the feature space. What is possible, actually, given a particular problem? It is not always easy to define a fitness function that will drive the search towards the solution we are interested in. It may be much more comfortable to actually explore the space of possible designs and then select afterwards the most relevant ones. So it was the motivation of MapElite, one of the first quality diversity algorithms. And it was for this reason called illumination algorithms, because it illuminates the space of possibilities and allows the designer to select afterwards. A second motivation, once you have this set of solutions, comes from what has been done in the multi-objective field. In multi-objective optimization, an approach has been proposed by Deb and Srinivasan that is called innovization. So the idea is to generate a set of points, and so the set of points is the Pareto optimal solutions that are generated with multi-objective approach, and then to analyze this set of points. By finding regularities in this set of points and understanding how they are connected and their relations, we can extrapolate and find a new and potentially more interesting solution that goes beyond the boundaries that we have selected. So that's something we can get from the generation of a set of solutions instead of a single point. But there are other advantages, other possible use. For instance, in robotics, it may be very useful, and there are more and more work about this, to use these approaches to generate a repertoire of behaviors. So the idea is to generate not a single behavior that could be optimal with respect to a fitness, but to generate a repertoire of different behaviors and then to select in a particular situation the most fit behavior. So that we learn offline, we generate this large set of solutions, and then online we just perform a fast selection of the most fit behavior. So that allows a process in 2 steps, one slow step and one very fast step. But there is another reason that is maybe less straightforward, and that consists in trying to find most optimal value to improve the performance of the process. And that's not straightforward, because if we are trying to explore the area, it may seem less intuitive that it may be a good way to converge towards better solutions. But this is something that is very important. Actually, in the case of complex fitness landscapes, with a lot of ruggedness, with a lot of local optima, exploration may be a difficult issue. It may also be the case in deceptive fitness functions. In that case, then the better thing to achieve is to explore, and then once we have explored, we can just observe where the optimal area is. And we can better illustrate this with some work coming from this pig breeder experiments. So in those experiments, an interactive evolutionary process was used on a platform called Pig Breeder to allow users to evolve pictures that are generated thanks to CPPNs, so continuous pattern producing networks. And those CPPNs are so networks with a specific activation, with different activation functions that are used to generate the images. So each pixel is given by the value of the CPPN once we provide as input the coordinates of the pixel. So this platform was meant to show the capabilities of those CPPNs to generate complex structures. But it is interesting then, once we have generated one, to look at whether it is easy or even possible to generate it through more classical objective-based search. So this is what Mouret and Stanley have tried to achieve. So considering a particular image, so here the skull, they have tried to reproduce it with objective-based search. So they have defined a fitness function that measures the distance in pixels between the generated image and the target picture, and they have tried to maximize this fitness. The results that they have obtained are plotted here. So they are very far from the real image. We can just generate here the global shape, but the internal structure of the skull has not been generated. Although it has been run for 30,000 generation, which means more than 4 million evaluation, which is really large. If we look at the number of generations that were required to get that results, we have something that is more around 1,000 evaluations. And here are the intermediate steps. And what is interesting is to see that actually it's very difficult here to realize that those are the intermediate step towards the skull. It is clear that none of them represents a progress in terms of fitness towards that skull. So that's an illustration of a deceptive fitness that may appear when evolving complex structures. To deal with this issue, a solution that drives towards solutions that are much closer to the complex structure we are interested in consists in generating this diversity of images. So starting from the same kind of process, but instead of trying to just maximize the pixel-wise distance, it is possible to use quality diversity to generate a diversity of picture and then to consider this pixel-wise distance only as a local distance. And it leads to images that are much closer to the initial image. So these are the different motivations to consider the evolution of diverse solutions. Now, let's go into what quality diversity is in more details and how we can generate those set of solutions and what they are actually. So first, we will consider the evolution of behavioral systems. So it may be in robotics, it may be in video games, it may be physical systems. So most of the time we are using the genotypes to describe this robot, this agent of this physical system that will interact with this environment. The interaction of this environment, starting from some initial condition, will lead to a particular trajectory in some relevant space. And this trajectory is what actually makes sense to estimate the fitness. This is this trajectory that we will consider and that we will compress into a behavioral space that is useful and that is interesting to explore. So now let's define what interesting solutions are. So as we said, as usual in evolutionary method, we consider a genotype space. This genotype space will describe a policy, which is a function that associates states to actions, so that this is what will make our robot or agent move, but it may also describe the morphology of our system. And the evaluation of this genotype consists in using the phenotype to control the system and to observe the trajectory it generates in some particular situations. Once we have observed that, we generate this trajectory associated to our genotype, and this trajectory is then projected into a smaller dimension space that is called the behavior space. So this trajectory is in large dimension, so there may be several thousand points for the different steps we have considered. So we need to project it in a smaller space to better understand what happens and to push towards a better exploration of it. So we project it into a small dimension behavior space, and the goal of quality diversity is actually to explore that space. So this is what quality diversity is about: finding a set of solutions, a set of genotypes that will cover as well as possible the whole reachable behavior space and with a good quality. So here each point in the behavior space comes from a particular genotype, but there may be different genotypes that end up in the same behavior here. And so among those solutions, we will be interested in those that have the highest local quality. Okay. So it will define quality diversity. We look for a diverse set of solutions that covers the reachable behavior space that are as good as possible. Okay, so now how do we reach that goal? A key feature to understand how those algorithms work is the evolvability. So evolvability is the capability of a system to generate adaptive phenotypic variation and to transmit it via an evolutionary process. So here it is very important because we need to explore the space of possible behaviors, and we need to explore it as well as possible. We need to cover all of that. So the ability to generate variations in that space is really critical. So we will consider two families of quality diversity algorithms that are based on different principles to generate that evolvability. So the first strategy is based on novelty search, and the second strategy is based on map elites. So let's look at this first strategy. So novelty search is actually a seminal work for these quality diversity approaches. It has been proposed in 2010 by Lehman and Stanley, and they just proposed to remove any goal-oriented objective and to replace it with a measure of a distance of a particular solution to its nearest neighbors in the behavior space. So that's very original because that's the first time that we remove that goal-oriented fitness and that we consider exploration as the main driver for the search. So we compute that the average distance towards the nearest neighbors in both the current population and an archive of the behaviors that have been generated before. So it may be random samples from past generations that are typically those having a high novelty, but that's not the only possibility. We could also select the random ones that has been done before, after. Okay, so what does novelty search perform? A very interesting feature of novelty search is that actually it tends towards a uniform sampling in the behavior space. So actually sampling in this behavior space is not straightforward. If we look at random genotypes and where they are projected into the behavior space, we can observe that they cover only a very small part of the behavior space. So here we are considering this maze navigation problem in which novelty search was first tested. So this is a problem in which a two-wheeled robot has to move around, starting from a position here, and one of the goals was to reach an exit here. So this is a deceptive maze, and if we follow a fitness here that measure the distance toward the exit, then the search gets trapped into this dead end. So if we consider just randomly generated solutions, we explore only a very limited part of the behavior space. But if we explore using novelty search, then what we observe is something that is much more uniform over the space of possible behaviors, which is very interesting. And if we observe the number of samples generated in each of those different red squares, we observe that the numbers converge to the same values, which means that after a while, we have generated the same number of samples near the starting position, in the dead end, and near the exit here. Whereas we consider large areas here in red or these very small areas in blue. In both cases, we have something that converges towards the same value. So that's a very interesting feature because it's not straightforward to here sample uniformly in that space. We don't access, we have no direct access to this space. We just sample in the genotype space, and the mapping between the genotype space and the phenotype space is very complex. So how does novelty search achieve this goal? So we will present a paper this year in Gecko, in which we show that actually evolvability results from the capacity of novelty search to push the population to always move in the space. So if we look at the age of solutions, we can see that with novelty search, this age remains very low, which means that new solutions appear all the time. They are not staying in the population. So this is an elitist selection strategy, so they could stay for long. So if we use the fitness, we can see that the age increases along generations, but with novelty search is not the case. And if we observe the distance towards the parents in the behavior space, we can observe that this distance that decreases very rapidly with the fitness, for instance, stays very high with novelty search. So novelty search puts a lot of pressure towards always moving in the space. So this is what forces a high evolvability of the process, of the generated solutions. So how to perform and generate solutions with a good quality? A simple strategy consists in using a multi-objective approach in which we add a local competition objective to the novelty objective. So with this local competition objective, we will improve the quality of the solutions locally. And if we look at the archive, we will generate at the end, we will have a set of solutions with this good local quality, which is what we are looking for. Okay, there is a second strategy, a second family of quality diversity algorithms that will be presented in more details in the remaining of this tutorial, which is based on MapElite, and with this idea of considering a grid of solutions and making the competition local to each cell. So in this selection scheme, once we generate a new solution, we evaluate it, And if it ends up in an empty cell, the solution is kept. If it finishes in a non-empty cell, then the competition occurs and the best solution is kept. So the competition is only local to a particular area of the grid. So how does it work? So in this case, it is very likely that evolvability results from a founder effect identified by Lehman and Stanley in 2013, and in which solutions with a large evolvability will tend towards generating solutions that are far from their initial solutions. And these solutions are very likely to have no competitors. So they have more chance to spread and to survive, and thus forward spread the genes. Whereas solutions with a lower evolvability will stay around and be in competition with their parents and their relatives. So it creates a basic pressure towards generating solutions with high evolvability without any explicit pressure towards generating that. So that's a very interesting effect. And in the following of the tutorial, then Antoine will provide more details about those algorithms. And I leave him the floor now.
Welcome everybody. Thank you very much for attending this second part of this tutorial, and thank you to Stéphane for the introduction. So in this part, I will try to give you a practical sense on how to use qualitative diversity for your own application. The goal of qualitative diversity is to learn in a single optimization process a large collection of diverse and high-performing solutions. Like most optimization algorithms, the quality diversity algorithms start from a high-dimensional search space, very similarly to the traditional genotypic space. And then quality diversity will try to project this high-dimensional space into a collection of diverse and high-performing solutions. So here you can see that the collection we try to develop is actually structured according to a descriptor space that is used to define the different type of solution. And the goal is to maximize the coverage of this descriptor space. And then for every region of this descriptor space, we want to find the highest performing solution. So the goal will be to find as many as those green dots that you can see here in this slide. If we had to define a generic pseudocode for most quality diversity algorithm in the literature, this one might be a potential candidate. As I said, the goal of quality diversity is to generate a collection, and so here we start from this collection. And then a typical loop will take place, which is composed of 4 steps. The first one is stochastic selection. The selection can be considering solution from the collection or from a parallel population that is maintained. And then with the selected individual, we will generate some mutated copies. Crossover can also be applied in order to generate new solution. So the new solution are then evaluated on the task and then potentially added to the archive depending on the performance and the behavioral descriptor of each solution. So in order to build this collection of high-performing solutions, we need to record 2 things when we evaluate the solution. We need to measure the performance of the solutions, and we need to distinguish between the different types of solution. And for that, we will use a fitness function, like in most evolutionary algorithms, and we will use a behavioral descriptor that we can also call behavioral characterization that will be used to define different types of solutions. The fitness function is it's similar to most of evolutionary algorithms, so it's directly related to the task. And for instance, if you want to learn how to walk with a robot, you can try to maximize the walking speed of this robot as a fitness function. Or if you want to learn or to train an agent to play Atari games, you can use the I-score on this Atari, on the different Atari levels as a good fitness function. The fitness function is used to define when we have 2 similar types of solution, the solutions that we want to keep. So that's where the competition will take place. The behavioral descriptor, on the other hand, aims at defining what type of solution this new candidate belongs to. And it's not necessarily linked directly to the task, like the fitness function. Sometimes we can have a behavior descriptor that will be orthogonal to the fitness function. Sometimes it will be more aligned. So that's a concept of alignment between the behavior descriptor and the fitness. And it's also very likely that multiple solutions will have the same behavior descriptor. but not the same fitness value. And that's exactly in this case that we will use the fitness value to define which of those two solutions or those multiple solutions we want to keep. So here are two examples of applications. So for instance, if I want to use this hexapod robot and I want to learn how to move the different legs in order to control the robot and move in different locations. So here we have the starting point of the robot, and every blue dot that you can see is the final position of the robot after walking for 3 seconds. So here in this case, the behavioral descriptor will be the X and Y location of the robot. And here in this different task, which is a ball throwing task, the behavioral descriptor will be used to characterize the type of trajectories and the location where the ball is landing. And here you can see that we will have a different type of behavioral descriptor because it will be defined according to the key points of the trajectory. So then I will move on to different blocks of the generic quality diversity pseudocode, and I will mainly focus and give more details about the container, the type of containers that are used to store and maintain the collection. And I will also give some details about the selector or the selection operation that are taking place. So in the literature of quality diversity, there are two main ways to store the collection. The first one is to use a grid, mainly from the map-elite algorithm, and the second one is to use an unstructured archive. That is a concept that comes from the novelty search algorithm. So first of all, the grid container. So as I said, we use the behavioral descriptor in order to define what type of solution it is. And in practice, the behavioral descriptor is nothing else than a multidimensional numerical vector. So with this numerical vector, we have vector space, and we can simply discretize this vector space into a grid, either by defining a certain length of the different cells of this grid, or we can also, if the vector space is bounded, we can define a resolution, so typically a number of discretization per dimension, and which will define the grid. Then what is important is to know how we decide to add and to maintain a solution in the grid. So the addition mechanism is relatively simple. Each solution goes to the cell corresponding to its behavioral descriptor. And then we have two possibilities. Either the cell is empty, and in this case we simply add the solution in the grid. And in this case it's actually good news, because this means that we extended the coverage of the collection generated by the quality diversity algorithm. Or the second case is when the cell is already occupied, and in this case we will simply keep the best solution between the two. In the case where the new solution is better, we had this new solution in the grid, and we remove and we delete the former one. And that's a good news, because this means that we improve the quality of the solution contained in the archive. So in terms of hyperparameters, we just need to define the size of the cells or the resolution of the grid. So it's a quite good advantage that it's actually very simple to implement, but the drawback is that you can also, or you have no way to ensure uniform density of the solution. For instance, we can have 2 points that are actually quite close to each other because they are just on each side of the same boundary, which might be sometimes problematic. The second type of container is the unstructured archive. The idea here in this case is that the solution will go directly and precisely in the location where defined by the behavioral descriptor, so not something that is approximated or discretized according to the different cells of the grid, but directly to the location. And then the addition mechanism will consider if the solution is actually, or if there's so this is the solution, and it's added to its exact location defined by the behavioral descriptor. And if this position, or if the closest solution is actually further than a predefined distance L, then we will add the solution. In the other case, if there is an overlap between the new solution and the closest one, then we will run a competition, and only the best solution out of the two will remain in the archive. So here, that's the main principles, but in practice it's slightly more complicated, because from some of our experiments we have noticed some erosion problem. The fact is, in some cases we might have a specific structure of the fitness with respect to the behavioral descriptor space. So for instance, we can have a case where the higher, so here in this portion of the behavior descriptor space, we might have a higher fitness, and the more we go to the right, we might have a lower fitness, which means that it will be very likely to have a solution here that will be actually with a better fitness, and that will remove the solutions that are actually further from all the rest of the archive, and that can continue until reaching here and have a continuity in the different solutions that are contained in the archive. Of course, here the quality diversity algorithm will have an opportunity to fill this region back, but this will naturally slow down the coverage and the exploration process of the quality diversity algorithm. So in some of the implementation available online, you can find a technique developed in this paper where we use an epsilon dominance Pareto concept in order to ensure that the solution is added only if it's improving at the same time the novelty, so pushing new solution further from the existing one, and at the same time improving the performance of the solution. So if we replace one solution by another one, we need to move further away from the nearest neighbor solution, and we need to have a better solution than the existing one. So here it's this region in this domain. However, in practice, it's very difficult to find a new solution that will satisfy both of those constraints in one go. So that's why we use the epsilon dominance in order to enable a solution to be a little bit worse in one of the two objectives, as long as it's actually be higher providing some improvements on the other objective that is higher than the decrease that is causing on the first objective. So this is what is represented in this graph with the novelty in one dimension and the quality in one dimension, and we only had a solution as a solution I2 if it's in this green region, otherwise we don't. And this solves the erosion problems that we have observed. The good thing with the unstructured archive is that it's maintained a maximal density because of this L minimal distance between the different solutions. On the other hand, the issue is that it's slightly more difficult to implement, and it has more hyperparameters, in typically the L value and the K value used to compute the novelty score. The second block of this loop is the stochastic selection. The other block of this main loop are actually very common in especially the random mutation and the evaluation is very common to standard evolutionary algorithm. And for the tentative addition to the collection, it's actually directly related to the addition mechanisms that I just introduced for the grid container and for the unstructured archive. So if we focus on the stochastic selection, the simplest way to do that is actually quite effective is to uniformly and randomly select a solution among the solutions that are contained in the container. And this way we can have a uniform exploration starting from solutions that are already found to be either novel and diverse compared to the rest of the population or of the solution, and that has been the best solution found so far for this solution. So that's the reason why just a uniform random selection over the solution contained in the container is actually a quite effective solution. An alternative, instead of doing a uniform selection, we can make a selection that is biased according to some metrics. So for instance, we can bias the solution according to the fitness. So for instance, here the yellow region has a higher fitness, so maybe we can focus on on selecting solution in this area. Another solution can be to explore or to prioritize the selection of a solution with a high novelty, because it might be in a good direction for the exploration. And finally, we can also use a curiosity score to bias the selection. Instead of selecting solution according to solutions that are already contained in the archive, it's also possible to maintain a parallel population. That's, for instance, what is done in novelty search with local competition. But in some cases that we have observed, it's actually more effective to use the solutions that are contained in the archive, mainly because they consider a larger diversity of solutions, so a larger number of stepping stones to start from and jump to for the rest of the expression. However, there are also some cases where population can have an interesting dynamics that can be more useful as well. So in the previous slide, I mentioned the curiosity score. So the curiosity score aims at finding or promoting or individuals that are present in the archive that when they are mutated and generate offspring, those offspring are quite likely to be added in the collection. And so in order to implement this system, it's relatively easy. Every solution is assigned a curiosity score. When the solution is newly generated, the curiosity score is set to 0 here. And then every time this individual here is selected and produce an offspring, and if this offspring is added to the collection, we will simply increment the curiosity score of the parent individual by +1. If the offspring is not added to the collection, the curiosity score is decremented by 0.5. And by selecting the solution in the archive proportionally based on the curiosity score, we will actually favor solutions that are that has a higher propensity to generate offspring that will be added to the archive. The interesting aspect with the curiosity score is that it's a dynamical score that changes over time during the course of the evolutionary process. Because at some point when, for instance, an individual will land in a completely new region of promising solution, it's very likely that all its offspring will generate or that will be generated will be added in the collection eventually. And this will in turn increase the curiosity score, so make this parent individual be more likely to be selected, so to generate more and more individual until this new area become completely covered and full, and in this case then it will be more and more unlikely to generate new individuals that will land in the grid or in the container. And in this case the curiosity score will decrease, and eventually this parent individual will not be interesting anymore, and some other regions of the archive and the collection will become more interesting with respect to the curiosity score. Some other approaches exist. So for instance, we can use a population of solution in parallel to the archive, as I said. But from some of the experiments, we have seen that it's working better. So for instance, here you can see different techniques, so either not doing selection or using a novelty score and a local competition score, or using randomly over the archive, or using the curiosity score. We can have different value. What we also observed is that sometimes focusing on specific heuristics or metrics like the novelty or the fitness might have some undesired effects. So for instance, leaning the exploration only in the local optimum or deceptive region of the search space. But in some other cases, you might have some interesting dynamics when using alternative methods like population. So for instance, Stéphane has a paper about why in this kind of system we have the availability that is inevitable. So that will be a talk at Gecko this year with some fruitful information. So now that I have introduced a little bit the main building blocks of quality diversity algorithm, I would like to focus on specific instances of those algorithms, and namely a map-elite algorithm. The map-elite algorithm is a combination of the grid container with a uniform random selection. The very good aspect with map-elite is that it's very easy to implement, and it's in practice a very powerful algorithm. Every time we try to find something that outperforms significantly map-elite, it's actually quite difficult, because if we give it enough evaluation to run, it will eventually catch up with the most sophisticated approaches, which is a very interesting phenomenon in practice. So how does it work? The first thing is map-elite has an initialization process. We start by randomly generating some random solution, and we add them to the archive according to the addition mechanisms that I have introduced for the grid container. After this initialization, we have an archive like this one with some solution in a couple of cells. So then we use a uniform random selection. We randomly select one of the existing solution, so let's say this one, and we generate a mutated copy. We evaluate this solution. during the evaluation, we measure the fitness and the behavior descriptor. And from the behavior descriptor, we will add this solution, or we will move this solution to the corresponding cell. If the cell is empty, we add it, like in this case. But if the cell were to be actually already occupied, we will use a fitness value as a competition mechanism to select which one of the two solutions we will keep. And simply by repeating this selection, mutation, evaluation, addition step multiple times, and when I say multiple times, often it's millions of times, we will eventually have this kind of large coverage of the different cells of the grid with a high performance on each cell. So for instance, this is an example that has been used in order to generate this kind of grid, where you can see that the color corresponds to the thickness of the individual, and we have some nice structure here. And I will go back a little bit more in details about this example in a minute. Now the question is, how can we quantify the performance of a quality diversity algorithm? So there are multiple aspects that needs to be quantified here. The first one is diversity of the solution contained in the collection. The usual metric that we use for that is the archive size. So because both the grid container and the unstructured archive container impose a minimal distance, or at least a minimal distance between the solution. So either thanks to the grid mechanism or thanks to the L distance. If we have a large number of solutions in the container, this means that we have large coverage of the different types of solutions that exist. So this means that we have a high diversity. So this is this kind of values that you can see in the archive size graph here. The second main aspect that needs to be quantified is the performance of the solution contained in the collection. So for that, we can either use the performance of the best individual, so the max fitness that is contained in the collection, or we can also compute the average fitness value across the solution contained in the collection. What is also interesting when comparing different quality diversity algorithms is the convergence speed about those 2 points. So how many generation or evaluation are required to reach this level of mean performance of this archive size, for instance. Often, in quality diversity literature, those two aspects, diversity and performance, are gathered into a single score that we call the quality diversity score. It's defined as the sum of the fitness of all the solutions that are contained in the archive, assuming that the performance are strictly positive. So in this case, having more solutions, even if they are weak, would be a good thing, or having very, very good solution would be also a very good thing, but obviously having a lot of excellent solution will be the best way to have a high quality diversity score. So the diversity and the performance represent two objectives that we try to solve at the same time, and necessarily this means that comparing algorithm can also be done by using a Pareto front. So for instance, here we have a 2D representation of the archive size matrix and the mean archive fitness, and we can rank the different variants of quality diversity according to this. And here, for instance, you can see 3 different variants that are on the Pareto front, so that represent a different trade-off between high diversity or high performance. So now I will go through a couple of example applications. The first one that I would like to talk is about how we can use quality diversity to, for instance, enable a robotic, like an hexapod robot, to learn how to walk in multiple directions. So here in this case, we use the unstructured archive with a random uniform selector, and the behavior descriptor is the X and Y location of the robot after walking for 3 seconds. The fitness here, because we want to encourage the robot to follow this kind of circular trajectory, is the orientation error between the tangent to the circle going or starting from the same initial location and ending to the same final location, and we compute the tangent to this angle as a fitness value. So as a result, we obtain this repertoire where every green dot represents a different control, so a different solution that is contained in the collection, and the difference between the two bars here represents the fitness value. So what you can see is that we have explored all the different directions that the robot can do. But when we did this, we tried to see also, because if the goal is to generate a lot of different solutions, we can also use or think about using independent learning processes in order to learn each of the solution independently. And what our experiment found is that learning all the solution in a single learning process, thanks to quality diversity, is actually way more efficient. So here the sparseness represents the uniformity or uniform coverage, how good the coverage of the reachable space is done. And you can see that using a BR evolution algorithm, which is a quality diversity algorithm, is actually significantly faster than trying to learn each solution one by one with independent learning processes. Another task with the same type of robot is to try to say, okay, I would like to go or to have my robot working as fast as possible on a straight line, but I would like to find a lot of different ways to solve this task. So in this case, the fitness is the working speed of our robot in a straight line, and the behavior descriptor is what we call the duty cycle. So that's the proportion of times that each leg is in contact with the ground. And after running the map-edit algorithm, what we found here is that the algorithm managed to find more than 13,000 different ways to walk. And in this picture here, what you can see, as I said, is that every colored pixel is a different walking gait. And the color of each pixel corresponds to the velocity of the robot. The more it's red, the faster goes the robot. And here, as you can see, the algorithm found not just a couple of a few controllers that have high velocity, but actually a large number of solutions with a high velocity. And what is quite interesting with quality diversity is that it's actually quite creative. So as I said, the algorithm found more than 13,000 different ways to work, but for instance, some of them are quite surprising. So for instance, here is the robot found a way to flip on his back and to continue to work on his knee, because that was another completely different way to work with a quite decent fitness value, while having a completely different behavioral descriptor representation. And this creativity of quality diversity has been observed in a lot of different applications. So for instance, in this other example, we use quality map-edit in order to learn how to push this cube with this robotic arm in a lot of different places around the table. So the behavior descriptor is simply the final position of the robot, and the fitness was to try to minimize the efficiency, the energy consumption when doing this task. And because this task was designed to be just a pushing task, we thought that there would be no need to control, and so namely to open and to close the gripper. So the robot here in this task is forced in the closed position and has no way to open or close its gripper. When we designed this task, we thought, well, it's just a pushing task, so it's normal if the robot is not able to grasp the cube and lift it in the air. But actually that was just a wrong intuition, because in practice the robot found still a way to grasp the gripper, so simply by forcing the cube to be blocked in one position and then smashing it from the top in order to make it fit in the gripper. Here is another example where the robot smashed the cube from the side, and again to make it fit into the gripper anyway. So that's two examples, but actually many other exist of the creativity of this diversity and divergent search aspect of quality diversity algorithms. Another big domain of application of quality diversity algorithm is for content generation, and in particular in video games. So for instance, in this example, the map-edit algorithm has been used to generate different type of level for bullet hell games. The idea is to provide a large diverse experience to the players by generating levels with a different level of difficulty, and that needs a complicated or sophisticated strategy, or also high degrees of dexterity and be very accurate in the movement. In order to generate this, the author proposed to use map-edit with a feasible-infeasible approach to ensure a constraint satisfaction. In another example, again for content generation, here in this work, the goal was to use map-edit in order to generate a dungeon design into a software to help designing this kind of level for video games. And what is quite interesting is that in this task, they combine this with user interaction. So in this system, the user can dynamically interact with the map-edit system in order to choose different behavioral descriptor definition depending on what is most interesting for the current design task that they have at hand. Another example is the generation of adversarial examples. So for instance, in this work, they used map-edit algorithm in order to generate artificial images, and they use a pre-trained neural network that has been trained on a large data set, namely the imaginary data set, and they trained the neural network for a classification task, and they use the label that is outputted by the neural network as the behavioral descriptor. And the fitness for the map-edit algorithm is a confidence level of the prediction of the network. And what is interesting is that all the images that are displayed here have the network with a confidence higher than 99%, so a very, very confident neural network. But on the other hand, when you look at the images, you can see that they barely resemble what they are supposed to be. Of course, we can imagine why the neural network think or is very confident that some yellow and black strips are a school bus, but it's definitely not the pure definition of a school bus. So it's a very good way to generate adversarial example to full neural networks in this case. There are a lot of many examples that unfortunately I cannot cover in this tutorial, but we have set up a website called qualitydiversity.github.io. It's meant to be a community website where everything is based on a GitHub repository. It's based on independent GitHub organizations, and anybody is welcome to join if they want to contribute. And if you want to add your own favorite paper to the list of papers that we display on this website, feel free to just raise a push request or an issue on the GitHub repository, and we will be more than pleased to add this contribution to the list of paper. Or we also have examples of tutorials and implementation and libraries available online. So now I will touch on some more recent concepts, because the recent popularity of quality diversity led to a lot of different research directions to try to improve those basic concepts. The first things that I will mention are some advanced container, mainly the container with sliding boundaries and hierarchical containers. And I will also talk on some recent research on attempt to automatically define the behavioral descriptor definition from high dimensional data or sensory data. So a paper has proposed to use map-edit but with sliding boundaries. This means that instead of using cells with a fixed size, we can adjust the size of the cells depending on the distribution of the evolved and produced individual. This is done by having a buffer that contains the last n individuals that have been generated and evaluated in a queue data structure, and then periodically redefine the boundaries according to the boundary of the cell according to the distribution of the solution. This has the advantage of allocating more cells, so a higher density of cells in an area with a high distribution of individual, and contrary in the other direction to have larger cells when there is less individuals that are generated in this space of the behavioral descriptor. Another approach is to try to use hierarchy of collection, because in one aspect is the behavioral descriptor space can become a new action space. So in a sense, we can use solutions that are contained in the first collection as some primitive solution in order to build more complex solution, and we can build like this on top of other collection in order to build more and more complex solution. So for instance, this is something we use with a robotic arm in order to learn multiple tasks and eventually learn a complicated task of drawing digits. So for instance, with the first layer using the map-edit algorithm, we can train a highly redundant robotic arm in order to reach any point in its vicinity. So in this case, we have as a genotype that is just the 8 degrees of freedom position of the robot. The behavioral descriptor is the final position of the robot at the end of the motion, and the fitness is simply here to encourage the joints to uniformly contribute to the motion by minimizing the variance of the angular positions. And after learning how to draw and how to reach any point in the vicinity of the robot, we can learn how to concatenate the different points together within a second layer here in order to learn how to draw lines of different length and directions. Then we can extend this concept by saying, okay, now that we learn via the second layer how to draw lines, we can learn how to concatenate the line together in order to draw arcs and circles. And here it's a way to build progressively more and more complex, and a good advantage of this hierarchy of solution is that actually it maintains the dimensionality of the problem quite small, because we don't need to, or we can keep everything very simple and always build on top of the primitive actions that have been generated before. Through those different examples, you have seen a large diversity of different type of behavior descriptors. It can be the X and Y location of a robot after walking, it can be the X and Y and Z location of an object in the scene, it can be some information about the interaction with the ground, it can be even something more complicated when we have a hierarchy of solution. And there have been some work in order to try to make the definition of the behavior descriptor a bit more automatic. So for instance, in this hierarchical repertoire task, what we wanted to do at some point was to draw digits. But actually sometimes the task is quite difficult, so that we cannot find a low dimensional representation of the tasks that can be manually defined. So what we decided to do instead is to use a dimensionality reduction algorithm in order to transform a high dimensional data into a low dimensional representation that can be used as a behavioral descriptor definition. So in practice, what we have done is that we use the NNIST dataset, which is a dataset of handwritten digits, and we train an autoencoder, which is a famous techniques to do dimensionality reduction systems. And what it does is that it learns a latent space where all the different type of digits are grouped and clustered in different regions of the latent space. So for instance, here you can see that all the ones are here, all the zeros are here, and so on. And then we can use, after pre-training this representation, we can use our standard map-it algorithm with this representation. So if my robot draws this kind of trajectory, I can transform this into a black and white image, and I can feed this to the encoder to find where it's landed in the latent space. And I can use these 2D coordinates as the behavior descriptor. And then we can use the map-it algorithm in order to try to find one solution for every region or every position in this space. And in practice, this is what is obtained. So we have the robots that, thanks to this latent representation, that has been autonomously learned thanks to the predefined data sets. The robot learn how to draw any digit between 0 to 9. So you have seen a 0, a 1, here is a 3, and so on. In the previous work, we use a predefined data set to pre-train the autoencoder. In a work that we published last year at Gecko, we wanted to move a little bit further by using the content of the collection in order to train, during the evolutionary and quality diversity process, the dimensionality reduction algorithm at the same time. So for that, we use the solution contained and generated after the initial step of the quality diversity algorithm, so namely the randomly generated solution. We can use the sensory data, for instance, that are generated by the evaluation of the algorithm, and we can project them in the container. And we can use those information to build a data set that can be used to train the dimensionality reduction algorithm. By training the dimensionality reduction algorithm with this new data set, it will actually change the definition of the behavioral descriptor in the collection, which means that if we continue to run the quality diversity algorithm, it has potentially the capability to find and explore new region of this newly defined behavior descriptor space. And in turn, this means that we will have a new solution that will be added to the data set. And after a couple of quality diversity loops, we can go back to the training loop of the dimensionality reduction algorithm. And by alternating like this between quality diversity loop and tuning and refining of the dimensionality reduction algorithm, we can have the quality diversity algorithm finding all the diversity of solutions that are generated here. We tested this algorithm on two different tasks. The first one is a toy problem where we consider a ballistic task where we throw an object and we aim to generate this kind of ballistic task. And another one is an air hockey task where we try to interact with an object in order to generate different type of trajectories. And in practice, what we have observed is that the distribution of solutions that we observe when projected into a ground truth space match quite well the coverage of some things that we will have manually defined with some prior knowledge. This concept has been extended recently to, instead of just considering trajectory of the object or the robot, to directly use raw pixel data from cameras placed on the top of the scene or the agent. So for instance, here you can see with the hard maze problem that the robot learned how to explore the maze in every direction. In the case of the quadruped robot called Ant, we can see with the blue dot distribution that the robot learned how to walk in kind of every direction of the space. And the same thing with this manipulation task, where the robot learn how to push and move the cube in a lot of different locations. Finally, we can also use meta-evolution in order to find the optimal behavioral descriptor definition. In particular, here we consider multiple available definitions of behavioral descriptor, and the question is to find the linear combination that maximize an additional performance function, for instance, an adaptation capabilities, or maybe, let's say, generalization capabilities of a robotic task. In this case, they use a covariance matrix adaptation evolution strategy algorithm, CMIES, in order to generate potential linear combination of the different behavioral descriptor definition. And then the results on this auxiliary task, the adaptation capabilities, for instance, is used in order to drive the CMIES process. Of course, for every combination of a linear combination of behavioral definition, this means that we will need to generate a new repertoire to see how this newly generated repertoire will fit to the meta task. This can be quite computationally expensive, but here the idea is actually to keep in memory, to have a database that stores all the solutions that have been evaluated with the genotype, the phenotype, and all the behavioral descriptor for all the definitions that are considered. So that thanks to this, every time a new combination, a new linear combination of the behavioral descriptor is used, the content of the entire dataset can be reprojected into this newly defined behavioral descriptor space, and then automatically and quickly regenerate potential collections. So this is a work that will be presented this year at Gecko, so it will have its own dedicated talk. So this is the end of my part. I will now leave the floor to Jean-Baptiste, and I would like to thank you for your attention. And if you have any question, I will stay around for the end of this presentation.
Hi, welcome to the third part of this tutorial about quality diversity algorithms. So in this third part, I will be focusing on scaling up quality diversity algorithms, both in terms of number of parameters and in terms of dimensionality of the diversity space. So, and in the last part, I will give you a few ideas about the implementation and what is available. So scaling up to more complex tasks is essentially means accelerating quality diversity algorithms. So one first idea that was quickly introduced by Antoine before is that you can try to select your parents better. For instance, select for curiosity, for novelty, for fitness, and so on. The second idea that I will explain more in detail later is just to have better variation operators, because if you generate better mutations or better variations, then you need fewer variations to reach the same result. Then you can use surrogate models, especially when your fitness is very expensive, so you need fewer calls to the fitness function to do the same thing. And in terms of scaling up to high dimensional diversity spaces or behavioral space, we can use distance-based archives or using centroidal for noise tessellation to have a grid that is not necessarily an array, like a two-dimensional grid. So let's start with scaling a bit with better operators. So of course, mutation and crossover have a long history in evolutionary computation, and you probably know that one of the most successful approach for optimization is CMAS, which is interesting because it resamples a population at every step, does not really use crossover or mutation, and it adapts the mutation strength for each dimension by adapting a covariance matrix. So something that people have been talking a lot in your community is, can we do the same for quality diversity algorithms? Like, can we do something that mixes the idea of CMAS with map edits? It's not that straightforward because each niche or cell follows a slightly different gradient in map edit. We are like solving many tasks at the same time, so we cannot just move in the direction of the gradient. But still, we also want to derive some knowledge because we have a big map with a lot of solutions, so we should be able to extract some information from this map that we generate with a quality diversity algorithm. So we started to investigate this with a very simple model with Vasilis Vassiliades a few years ago. So we started with very simple model, which is a small arm with 2 degrees of freedom. The genotype are just the 2 giant angles, so theta 1 and theta 2, and the phenotype of the behavior space in that case is xy, or so the xy position of the end effector. What's nice with this is that because we have a genotype that's only 2-dimensional, we can plot the values, and we can do the same for the phenotype, so for the behavior space. So we run map edits on this problem, trying to reach all the points of the space, and you see the result on the top row. You quickly see that it's a circle because it's an arm, so you cannot reach all the points. The links are too short to reach the whole space. And it has some nice and smooth landscape, meaning that some situation with the fitness that we're using here, the fitness is not perfect. And the fitness that we're using here is the variance of the angles, but that does not really matter here. What's very interesting is that if we look at the genomes of these elites, the one we find at the end, so that's the second row on the right, you see that it has very specific shapes. That means that in the genotype space, the elites are not like well spread. They are occupying a very specific volume of the genotype space. So we can be very well spread in the behavior space and on a very specific volume in the genotype space. So this is what we call the elite hypervolume. And what that means is that the elites all have following some kind of recipe, some kind of pattern. So this pattern, as you see on the right, is not obvious. It's not like a simple circle. It's not like a correlation between the 2 parameters, theta 1 or theta 2. But there is clearly a structure here. And if you think about it, we see similar things in nature. If you think that all of the cells of mapelids are like niches, which is an interesting metaphor, then you can understand that, for instance, one niche could be like a fruit fly, another one would be humans, and maybe another niche would be a monkey. And interestingly, if you look at the biology and the genomes, you see that, for instance, humans and fruit flies have 60% of their genes in common. So that sounds surprising because they occupy very different niches, like they live very differently. One of them is flying, like fruit flies. Humans are not flying, obviously. Fruit flies have like very special eyes, very different legs, very different scales. They're not even competing with humans most in the niches. So, but still, if you think about it, they're applying similar recipes, like the neurons of fruit flies are quite similar to the neurons of humans. You also have muscles, you have cells, so you have a lot of things in common. So somehow nature has found some kind of recipe and then applies similar recipes to all these different niches. So it's the same. In all the possible genes that nature could have been used, then they occupy a very specific subvolume. So we observe the same in mapelids. So we try to use this to try to generate better solutions with mapelids. So a good variation operator should be an operator that is highly likely to generate an individual in the elite hypervolume. So if you already have some solutions that are likely to be in the hypervolume, like good solutions for now, the best you know, then you should be able to generate something that is also in the elite hypervolume. A surprising thing is that we already know such operators and they are crossover operators. So if we take two elites from the hypervolume and we blend them somehow, if the hypervolume is convex, which is what we have on the left here, the circle, you see that you're guaranteed to generate something that is also in the hypervolume, so also an elite. So given two elites, you generate a new elite, which is quite useful. Of course, you don't know if your hypervolume is a circle or is convex. So if the hypervolume is not convex, then you're not guaranteed to generate something that is also an elite. But still, you're quite likely to do so. So on the right, for instance, you see the example that we used, and you see that if you take the points that we used here, then if you do a crossover between them, so something that mix them, then you're very likely to have you generate something that is also in the same hypervolume. So you generate a new elite. So we wanted to have like a simple crossover that is working well for this case. So what we did is to propose this directional variation operator, which is essentially you take two parents from your map, then you draw a line, and then you generate a random point in between them. So we're just taking a random value. And once you have this, you add some Gaussian perturbation. So at the end, you have distribution that looks like this ellipse that you see, like the third drawing. You can also use more classic crossover operators. This one is nice because it's very straightforward to use, very straightforward to implement, and still it gives a very good result in things we have tested. So we tested this on several benchmark problems, like the arm that I showed before, but more high-dimensional, six-leg locomotion in robots, the Schwefel function, which has obvious regularities, so we know the hypervolume. And the surprising conclusion is that crossover in general is very useful in this archive-based quality diversity algorithms, much more useful than what we thought at the beginning, and most probably more useful than in classic genetic or evolutionary algorithms. And one of the reasons is that we make the archive so that we have a good diversity, and then we try to model this, or not to model, but at least to create this elite hypervolume. So to me, that's very surprising because I never really believed in crossover, and I say we don't use it in evolutionary strategies, and still here in that specific case of quality diversity algorithms, it seems to be very, very useful. So in this situation, we tried, so in this example here, we tried SBX, which is a classic evolutionary, classic crossover for float numbers, and this directional variation, and both of them are really, really helping map elites to converge. So this next step, we say, okay, but if we have this weird shape, maybe we can model it, so that means that we can sample directly in that specific elite hypervolume. So of course, as you've seen, the hypervolume is not like a nice Gaussian. It's not it's not easy to model. So one modern way of doing it, or modeling this complex distribution, is to use a variational autoencoder. So the variational autoencoder, we look at the map, try to learn the distribution, and then you can generate new individuals that follow the same recipe, that are in the same distribution. So the recipe of successful individuals. The main problem is that's not that easy, because the autoencoder, especially at the beginning, when you don't really have the hypervolume, will just generate things that look like what you already have found, but it will not help you to find new things that are out of the distribution. But because you haven't found the distribution yet, the elite hypervolume distribution, then the autoencoder can help, but it's not enough. So there is an exploitation trade-off for the representation. And what we used in this recent contribution that is published in this Gecko 2020, and please check the video and the paper for this for details, is that we have two ways of improving the V-archive. One is to use the classic operators for map edits, so things like directional variation and classic Gaussian mutation, for instance. And the other one is to use the autoencoder to generate new solutions. And we get very good results in the task that we have investigated. So in that case, we still use the same arm, but we try to scale it up to 20D, 200Ds, and 1000Ds. That means 1000 degrees of freedom. And what we observed is that when we use the autoencoder, because it finds like the recipe for good solution, you can essentially use very high dimensional search space, and you mostly get the same result at the same speed as what we get with lower dimensional problems. And the reason is that it finds the recipe and then just applies it again and again and again. So please check the paper and the video in Gecko 2020 about this. Another recent contribution that is also published in this Gecko 2020 is to take a direct inspiration from evolutionary strategies. So in the simplest version of evolutionary strategies, at every generation, you sample a new population by adding a Gaussian noise around a mean. And the idea is that to get the new mean, then you take the other one, the previous one, and you multiply the fitness that you obtain by the perturbation, so that you essentially move in the direction of the perturbation biased by the fitness. It has been found recently that it's surprisingly effective for deep reinforcement learning, which is specific because you have thousands of parameters or even millions of parameters to learn. And so in a very recent paper, Cédric Collat and colleagues proposed an evolutionary strategy applied to map edits. And the idea is to alternate between two strategies. First, they sample a cell with the best novelty, so a cell that has few neighbors, and then they optimize for novelty with the evolutionary strategy. Or they sample a cell with the best fitness, and they optimize for fitness with this evolutionary strategy. And they alternate between these two strategies, and they show that they can pick the basic map edits operator in that case. I don't think they have tried the crossover operators here, which probably could have helped. But key thing is that when you look into this, if you have just a few evaluations to use, then you need to be careful about the biases that you use. So if you want to have very good fitness values and if you want to fill the archive. So usually when you just have a few generations, you cannot have full coverage and full convergence and everything. Still, I think that's very interesting work. You should check their video and their paper in Gecko 2020. Another contribution at this Gecko is emitter-based quality diversity with the paper called covariance matrix adaptations, which again takes inspiration from CMAS and tries to make map edits smarter about how to generate new solutions. So what they do here is that they have a small population of CMAS instances, and then they try to select one of them and then generate new individuals according to different ideas. So one is to say I take a random direction in the behavioral space and I try to move in that direction. Another one is to improve the collection, so improve the map edit. So that means that you rank individuals depending on how much they have improved the archive. This was recently improved by Antoine Cully with a paper called Multi-Emitter Map Edits, in which he uses a bandit algorithm like UCB1 to pick a different set of emitters at every generation depending on their effectiveness. So you can alternate between exploring or doing more exploration in the behavior space and doing more improvements. So again, the conclusion is that it seems to help, especially at the beginning, like if you have just a few generations, it helps to feel things better. I think more benchmarks are needed to conclude if all these approaches here, how do they compete together and what's the best, but also the simplest one to get the best algorithm. Second topic of this of this third part of the tutorial is what to do when your fitness function is very expensive. So quality diversity algorithms usually need designed to have hundreds of thousands of evaluations or even millions of evaluations of the fitness function, which is doable for many fitness functions on modern computers, but this is not possible in many applications that are really interesting. For instance, robotics, aerodynamics, anything that involve complex simulations, like mechanical simulation and things like this. But of course, quality diversity could be very interesting for engineering. For instance, it can be a very useful exploration tool to provide ideas about good solutions, and then the designers can pick up the design that they like using other criteria. So they already know they're good, but then maybe they like one design better because it's more aesthetic, for instance. So the classic solution in optimization in this situation is to use a surrogate model. The concept is that you use a few expensive precise evaluations, that means that you call your complex fitness function to learn a cheaper predictor. So it could be a neural network, could be a Gaussian process, these kind of things. And then you use the predictor in the algorithm, and periodically you add new precise evaluations so that you improve your model, and then you get your results usually by calling your fitness function fewer times. So we proposed something with Adam Geyer and Alexander Asterot a few years ago called SAIL for surrogate assisted illumination. And in that work, we use Gaussian processes to model the fitness, which is interesting because it gives a prediction of the mean, so prediction of the value of the fitness, but also about the uncertainty, which is modeled as a variance here. And the key idea here is that we need to choose what's the next point that we want to try to improve our model. So what we did here is that we look at something called the upper confidence bound of the Gaussian process, which is the predicted mean plus the uncertainty, which is high when a point is predicted to have a high fitness and also very uncertain. Could also be high if it's very uncertain, could be high if it's very likely to be very good, so if the mean is very good, and it's even better if both are combined, like high potential solution. So if you want to do this, but in the case of map elites or quality diversity, of course we want to do this for all the potential niches, all the cells. So what we did is that we run map elites with this UCB to fill a prediction map, so to find many good solutions that has a high value for UCB. And then we select the solutions to be evaluated on the expensive fitness function randomly from this map. And what we observed is that it's very effective when we try this on the problems, classic problems in optimization. So in that specific case, we tried to use airfoils, which is a classic domain, to test the surrogate models. And the results say that in only 1,000 precise evaluations, which is more or less the number of evaluations that we need for CMAES to find a good solution in a single bin, a single cell, then with SAIL we can fill the whole map and with similar quality. Another nice property of surrogate modeling is that we can quickly generate a prediction map at any resolution. So we can increase the resolution of the map for almost free, given that the model is considered to be free, but definitely much faster than most fitness functions. The main challenge if you want to use surrogate assisted illumination is that that does not scale well with number of parameters. So if your genotype space is very large, like if you have more than 10, 15, 20 parameters, then it becomes very hard to make predictions about the fitness given the parameters. And the other issue is that Gaussian processes are very good for surrogate models, but their query time increases quadratically in the number of samples. So after a few thousand samples, then it starts to be very slow, and that makes the surrogate much less useful. Another paper that was just published, not published, submitted, but I guess we publish soon, is what they call BOP elites. So in that case, they also use a surrogate model to try to do to solve the quality diversity problem, but they use two Gaussian processes, one to predict the niche and one the fitness. And then they try to use the expected improvement, which is, if you take a specific niche, what is the expected, how better you can be. But then you don't know exactly if a predicted value will be in that specific niche, so you need the second Gaussian process, and you can multiply the two to have the expected improvement for a niche, and then you can sum for the whole map to get the expected joint improvement of the elites. So to select a new point, you just run, you optimize this function, this expected joint improvement of elites. You can do it with any nonlinear optimization algorithm like C/S if you like. Then you will create, query your fitness function for points that are very likely to be good. And then you can use this to improve your model and then run it again until you have a very good prediction for the whole map, or you know a lot of elites. Second point that I wanted to explain in that tutorial is how do we scale up to high-dimensional behavioral spaces. So far we mostly use quality diversity algorithms in low-dimensional behavioral spaces, two-dimensional, but there are many high-dimensional behavioral or feature descriptions. For instance, trajectories of robots. Most of the interesting problems that you can think about, usually the two is very little to describe them, to describe the behavior of something. The issue is that if you start doing a grid, like what we do in map edits, if it's 2D, that's okay. Like if it's 500 by 500, that still gives a reasonable amount of cells. If you're in 6D, which is not that big, let's say that you do 5 bins per dimension, that gives you 15,000 cells, which starts to be big. But just increase this a bit, like to 12D, still 5 bins per dimension, that give you more than 200 million of cells, so that starts to be very, very big. And 36D and only 2 bins per dimension, it's like 68 billions. So we need to find a way to not use just a regular grid as we did in map edits if we want to use more high-dimensional behavior spaces. And essentially, we need to make the number of cells independent from the dimensionality. So I know two options to do this. One is to use distance-based containers. So in that case, we don't use a grid. We use a container based on the distance. So the idea is that the solution is added to the archive if the distance to its nearest neighbor is above a given threshold. So that means if it has no neighbors, essentially, or if it is better than its k nearest neighbors. So if it's better than things that are all around it. The main drawback of this is that you need to decide the different thresholds, so L and K, but then you don't care about the shape of your behavioral space. It doesn't need to be regular or whatever. So it does work well provided that you have a good intuition about the parameters that you need to use there. The second option, which is very close to map edits and that we published a few years ago, is to use something very classic in computer graphics, which is called centroidal Voronoi tessellation. So the result here is that we specify the number of cells, and then we get a grid with cells of equal volume. So you have an example on the right. On the top, you have the regular grid that is used by map edits, and on the bottom, you have a grid with 7 cells generated by CVT map edit. And it works in any dimension. Also, another nice thing is that it's already implemented in many libraries. So it's, of course, in computer graphics libraries, but essentially it needs only k-means to be computed. And k-means is a very classic algorithm. You have tons of implementations in every scientific library. And nice thing also is that we need to generate this once at the beginning, and then we use this as a grid, like in map edits. So this is an easy way of decoupling the number of cells to the dimensionality. We say we want 1,000 cells, and whatever the dimensionality is, we get 1,000 cells of equal volume. It's actually quite easy to implement. So general idea is that we just take a lot of random points, and then we run k-means on these points, and then that gives you what's called the Lloyd relaxation. And then you can get the nice drawing that you have on the right, which is the Delaunay diagram from the centroids, but actually you don't need this Delaunay diagram to run the algorithm. What you only need is to be able to say, okay, I have a new individual, I know his behavior description, in which cell does it belong, which is nearest neighbor query, and that can be easily solved in no-dimensional spaces using a KT tree, which again is available in most libraries, or in high-dimensional spaces. Actually, sometimes even better than the KT tree is just to sort by distance, which is like 2 lines of code. And using this, we can really scale up to high-dimensional behavioral description without essentially any change. Before concluding, I want to describe quickly a few quality diversity implementations. So let's start by saying that one of the strengths of current quality diversity algorithms is that they are easy to implement. The easiest to implement is a grid-based map edits. Potentially, I would advise you to use directional mutation because it really improves things in just 1 line of code. The most flexible one, the one I will advise you to implement, is CVT map edits. So using the for-noise tessellation plus map edit is slightly more complicated, but it's not that complicated. And the one way to know that it's quite easy is that most research groups implemented their own version. You don't need a specific library. So that's very good. It means that everybody can have their own version. That said, implementations can be useful if you want to start. That can give you good baselines, give you some complex options like a new version of new algorithms, and maybe have a better implementation, parallelization, and so on. So one implementation that is available is what I call the reference implementations. So here we have implementing in Python implementations of CVT map edits and multitask map edits that are designed to be straightforward. So that's like 1 page of code. And the idea is that you can just use this as a starting point to hack your idea. It's very easy to understand. It's just 1 page of code. So here's an example how to use it. But what I want to show is that's the whole code, everything needed for CVT map edits. And you see it fits on 1 slide. Okay, it's written with a small font, but still, if you read this, you will understand this very easily. It's almost like pseudocode. So the idea is that you can take this and change it the way you want. It's a starting point, so you can hack your own idea. A more fully featured framework is QDPI, which is also in Python, and that implements map edits, CVT map edits, but also more advanced algorithms like SAIL. And it provides many more algorithms, and it's a bit harder to hack, but also if you just want to use algorithms, it probably provides you with more options. Then there is a C++ implementation in Sphere 2, which is a generic framework for quality diversity, template-based in C++11, which is very, very flexible, but can give you access to the, it's very easy to define new algorithms and implement your own, but of course it's a template-based C++11, so there is a steeper learning curve. The main advantage over the Python version is that it's much faster, like 5 to 10 times faster in many situations. And it's not that difficult to use, so that's only how to use it here. Just to conclude, some ideas about open question and challenges. So we have a paper in this Gecko 2020 about the relationship between quality diversity and multitask optimization. So multitask optimization means that you want to solve many tasks that have some similarities at the same time. For instance, you want to learn to grasp many different objects like sphere, cubes, and things like this. And for knowing if you can grasp a cube, you need to query your fitness function for a cube. It's not something you can derive as a behavior description. But as we show, QDA algorithms can be modified for multitask optimization. And I think we should continue to investigate this relationship between multitask optimization and QD because multitask optimization is like more generic field, more impactful maybe. Another question is that we currently do not handle noise in the fitness well, but we do not handle noise in the behavior at all in most of the algorithms. So if you have a noisy fitness function, basically with an elitist algorithm like MapEdit, you have to reevaluate many times so that you just remove the noise. And I think we can do much better than this. We tried a few things last year with Neil Justensen and Sebastian Noisi, but I think there is much more to do. And the real challenge is the noise in the behavior space. More open questions. For now, we're using quality diversity, but without any gradient. If we have access to the gradient, can we use it? How can we make a quality diversity optimization algorithm with a gradient? And I don't know how to exploit high-dimensional maps, like how to show them, how to explore them. We can generate them, but what do we do with them? But more generically, I think the main question for the field is what are the good domains, the good application cases for quality diversity? I think we have found a few ones, like in games and robotics, but it would be very interesting to know more about in which field can quality diversity algorithms make a difference. So thank you for your attention, and I think we can take questions. Thank you.